To illustrate the derivative, I'm going to use an example. Imagine that I'm driving down to my grandparents' house. And let's say that getting to their house is a straight shot on the interstate. It's about 180 miles away. And so I want to draw an illustration on this graph of my trip down to my grandparents. Let's get rid of this title so that we have more room to work. So as you can see, I've already created a graph that is the distance I've traveled versus the time it's taking me to get down there. And so of course I start off right at time t equals 0, having driven 0 miles. And we're going to imagine in this ideal situation that I left early in the morning, let's say, and so I didn't have any traffic, and so I was able to drive a straight shot at exactly 60 miles an hour the whole time. And as a result, after 3 hours of driving, non-stop driving, I make it to my grandparents' house. So this graph simply represents the position as measured in distance from my house, the position I'm at any given point in time. And we can read off from that. Let's see, after an hour, where was I? Well, I've gone 60 miles. After 2 hours, I'd gone 120 miles. And after 3 hours, I'd made it to my grandparents' house. There's one other question I want to ask about this graph, and that is, what is its slope? Well, we all know how to calculate slope. Slope is just, let's fix that. Slope is just y2 minus y1 over x2 minus x1. And in this case, let's take our y2 to be 180 and our y1 to be 0. Then our x2 is 3 and our x1 is 0. So continuing that calculation, I just get 180 over 3, which comes out to 60. So I have a slope of 60. Well, what are the units for the slope? Well, it's the y over the x, and the y is miles. The x is time in hours. And so this is miles per hour. Now, as soon as you see 60 miles per hour, you realize that the slope is telling us something else about the trip, and that is my speed. I was driving at 60 miles per hour through the whole trip. Well, this graph is a little bit unrealistic if anyone has ever driven on the interstate. And so we're going to make a slightly more realistic drawing. In fact, I'm going to show you 3 example drawings that will gradually become increasingly realistic, and they'll help you understand better the concept of the derivative. So let's make the graph of my trip just slightly more realistic by allowing my speed to vary at different times in the trip. So let's suppose that I get off okay. Now my wife would tell you that that in and of itself is unrealistic because we never leave on time. But let's leave that aside. At any rate, I get off okay and I drive for the first hour without any issues, 60 miles an hour, no traffic. And then all of a sudden I hit, I don't know, some kind of slow down, more people are on the road, maybe it's raining, whatever. And so for the next hour, I only make 30 miles of progress. Well, now I'm getting very concerned because I promised my grandparents that I would get to their house at a specific time, And so now I need to really hot foot it. And so I throw caution to the wind and make it, let's try to get this graph right, make it 90 miles in the last hour. All right, there we go. Now let's ask the question that we asked before. What is the slope of this graph? Well, if you think about it, it's a little bit nonsensical because this graph is not a straight line, and therefore we can't talk about it having a slope. On the other hand, we can talk about an individual segment having a slope. This piece from here to here, for example, looks like a straight line, so we can talk about the slope for that segment of the trip. Instead of writing y2 minus y1 over x2 minus x1, I'm going to use slightly different notation. Sorry about that. And I'm going to write this as delta y over delta x. How much did the y value change and how much did the x value change? Well, the y value at the end of the second hour was at 90, and at the beginning it was at 60. And the time at the end of the second hour was 2 hours, and at the beginning it was 1 hour. And so what I get is 30 over 1, which, as we know for the units based on the previous example, tells me that during this interval I was driving 30 miles per hour. It would be different for the other intervals, but for that particular one, it's easy enough to define my speed. Okay, well now let's do the most accurate example that we can about what it's really like to drive to the grandparents. And so what really happens is, again, I'm just going to still assume, even though it's not realistic, that I start out on time. So I go out, but my speed varies. In fact, I get to here and I decide I need to stop in at the Wendy's and get some fries and a, what are those things called? Frosty. And so I don't make any progress at all here, and so then I start really speeding. And finally, in desperation, as I realize I'm not going to make it, I decide to try a shortcut. Only problem is I've never tried this shortcut before, and it actually ends up taking me backwards. By the time I realize it, it's really getting late, and so I have to go at a speed that I would rather not discuss in order to get to my grandparents on time. So that's a little more realistic. My speed is continuously varying, and that's reflected in the progress or lack thereof that I make as I drive down to my grandparents. So let's ask the same question we've asked before in the previous two examples. What is the slope of this curve? Well, if the question seemed a little odd in the last example, it's truly puzzling here because we don't have any straight lines. And so we're really asking, what is the slope of a curve? This became a very important question about 400 years ago. And a great deal of effort was expended by a good deal of intelligent people trying to answer the question, what is the slope of a curve? Well, finally, it was collectively figured out that there's a trick to finding the slope of the curve. And that is, let's suppose we just pick a particular little segment in the curve, just this area here. And we blow it up, and we notice something about the blown up portion of the curve. And that is While it's still a curve, when you blow up just a little piece of it, it's a lot straighter looking than it is when you're looking at the general graph. And the fact of the matter is, if you were to keep blowing this curve up, portion after portion, keep zooming in and blowing up smaller and smaller portions of the graph, it would come closer and closer to looking like a straight line. And then we would be able to calculate how much y changed and divide by how much x changed. The only problem is, the only way to get a perfectly straight line is to blow it up infinitely, and then the change in y is going to be 0, and the change in x is going to be 0. And we've been taught for years, and our TI calculators reinforce the fact that 0 divided by 0 is simply undefined. And yet that doesn't sound quite right, because we think, well, wait a minute, this is an actual trip that someone took. At any given instant in time, the person was driving at some speed. The speed certainly wasn't undefined. And so there must be some way to tease out how 0 divided by 0 can be an actual number. Well, that's what's going to come up here. And what we're going to do is we're going to define the slope, not between 2 points, but the slope at a point. Now I know that sounds a little bit like the sound of one hand clapping, but in fact, we will be able to find the slope at a point. We will be able to figure out what 0 divided by 0 is, and we're going to give a name to that result. We're going to call that the derivative. And that's the first key concept of calculus.